Okay, good morning to the people here. Um, my name is Nicholas Crouch. I work in the Maths Learning Centre at the University of Adelaide. This means that I'm not actually associated with the School of Economics or the Faculty of whatever it is, Faculty of Able, Arts, Business, Law, and Economics. And so I'm not actually part of the teaching team for your course. I know this course quite well. But I don't actually sort of teach this course. So the advice I'm about to give you is about from the point of view of the correct mathematical advice. It may not be directly in line with what your lecturer has said. That said, I've spent a bit of time trying to look over your course notes to make sure that the things I am telling you align with what you've been told in the course. So we've had a request to talk about sort of doing a bit of Gaussian elimination and showing the rank of a system. And so I'm going to try and start at that point. And then from there, we can go through and try a few other things. So the first thing I thought I'd do is, possibly before I get to that part, should point out you can come and talk to us in the Maths Learning Centre about any of these topics. And we welcome you to talk about any of the maths that crops up in your course, particularly you guys, because you are clearly doing economics. And so there is some maths in economics, and we can help with the maths in the economics. Even just the way economics write stuff is quite mathematical. And so we can actually talk, if just helping you read through the notes for what's actually in the notes can actually help. I've found over the years, because every so often people go, hey, what did they want? And I'm like, it's not maths, but I can explain how they're using that term. So without much further ado, there's apparently a sample test. Yaping has put up a sample test for this semester. So, maths learning. So if you do maths learning at adelaide.edu, so maths with an S. You can email us questions at mathslearning at adelaide.edu.au. And hopefully I will have a sample exam to talk about in a second. What I'm going to do is I'm just going to, I've grabbed one of the textbooks I have lying around. I'm going to just switch to sharing my camera now. So you'll see we have a pile of questions. There are things like this where I'm not going to try and go through that. That's a lot of work. But so there are some system of equations, and I thought what I might do is I might try and take a couple of these and just work out what's going to happen if I try and do this. So just to see what's going to happen. One of the interesting ways that your course deals with, hang on. Did I remember to do this thing? Yeah, beautiful. All right. So if I'm given a system, so quite often you guys are going to start with taking a system of equations. So for example, x plus 2y plus z is equal to 2, and then 3x plus 4y minus 2z is equal to minus 2, and 2x minus z is equal to 2. As an example. You'll notice that I've tried to line up my x, y's, and z's, even though there's no y in that last equation. I've just left it blank. That's kind of a good idea because it's going to help you. You can sort of read off that matrix A that we're going to get is going to be that matrix of coefficients. And so that kind of says there should be a 0 in that spot. And so my matrix should look like 1, 2, 1, 2, 3, 4, minus 2, minus 2, 2, 0, minus 1, 2. All right. Technically, we have a little dotted line here. We have the thing. So when we're doing like our elimination, all right, we're going to decide on, we're going to try and choose the top. We want to choose something in the first column, and we ideally want to use the one in the top one. We want to make it 1. This one's already 1. Oops, I'm done. All right, I'm now going to add multiples of that row. So multiples of row 1 to row 2 and row 3 to make it so that it's 0. So I'm not going to change row 1 this time around, but I am going to make these two 0. Working out what I did to make that 0, row 2 is equal to row 2 minus 3, row 1, and row 3 is equal to row 3. So technically it's just minus that number. All right, because this number is 1, it's minus that number. And then I actually go through and do the row operation. So I had, this is going to be 4 minus 3 of this, which is going to get me 4 minus 6 is going to be minus 2. Minus 2 minus 3 is going to get me minus 5. Minus 2 minus 6 is going to get me minus 8. All right, sweet. And now I'm going to have, so my 2, take 2, 0, take 2 lots of 2, so that's minus 4. 1, take 2 is going to be minus 3. And I have 2 plus 4. It's going to get me 6. None of these numbers are happy. All right. All right. So this next stage, I've kind of got a thing where what I'm going to do is I'm going to ignore the row and the column that I've already, and sort of pretend I've got a smaller system. All right. And I'm going to repeat the process. So this would be my element that I'm focusing on. It's not 1. So my first process would, first thing, in actual fact, what I did is I looked at the row below and said, that wouldn't happen to be, I couldn't make that 1 easily, could I? Because I might be able to swap. Like if this was a 1, maybe I could swap the rows. But in this case, I'm just going to divide through by minus 2. So I'm not changing any of these other rows, so I can fill them in straight away. And this one, I'm dividing by, so it's row 2 is equal to minus a half row 2. So that's going to be 1, that's going to be 5 on 2, 2. That's a 2 if you didn't guess. And that should be 4. All right. Now, this is where we diverge. We can sort of diverge into row echelon form or reduced row echelon form. I'm actually going to go to reduced row echelon form because just to sort of make it easier for you. So I know, so that means I'm going to make this one and this element 0. All right. All right, you guys. This is where you go, hey, Nick, the picture's not on the screen anymore. All right. Because that's actually going to help me out a bit. Because sometimes I'm focused on the things I'm trying to say or the points I'm trying to make rather than doing the actual thing. The other thing is, probably should point out, I probably will make a mistake in the working somewhere along the line. Yes. Which is? Down here. Oh, 6 here. So do we think that that one there or the one above it? So if we go, if we're not sure about that value, so this is where we copied the matrix down. This is, so we did this row operation. So we said this number, take 2 lots of this number. And, oh. What are you doing to me, Nick? You're supposed to pick that up for me. This is exactly what I mean. All right, I will make mistakes about this. So we're saying we should have 2 minus 2 lots of 2. That should be minus 2. And so that should be minus 2. Okay, yes. All right. We should never believe my work. So fortunately, I do know how to do the maths. So what I did here is I did row 1 is equal to row 1 something, row 2. So row 2 is my pivot column. And so it's going to be something row 2. The row I'm working with is equal to the row I'm working with, plus or minus some multiple. And it's going to always be minus this number. So when I come down to this one, row 3 is equal to row 3, something row 2. Because this is minus 4, my minus 4 becomes plus 4. All right. And you can just, it's a very mechanical process. The reason we love doing this is I can program the computer to do this really, really simply. So if we talk about this element here, we have one, take two lots of 5 on 2. So that's 1 take 5 is going to be -4. We have 2 take 2 lots of 4. So 2 take 8 is going to be -6, hopefully. And down here, so when we're doing this, we've got -3 plus 4 lots of this. So 4 times 5 on 2 should be 10, I reckon. So -3 plus 10 should be 7. -2 plus 16 should be 14. Okay, so this, we could call this row echelon form, all right? This is enough for me to go after row reduction. I can see that I have 3 non-zero rows. And so that would mean the rank of this system would be 3. That is the maximal rank for this system, right? The value for the rank cannot exceed the number of rows or the number of the smaller of the number of rows or the number of columns. So if I had sort of something with 3 rows and 2 columns, the maximal rank would be 2. All right. It's an interesting, so the way you've talked about in lectures is if the rank of my system A is equal to the rank of the system with the augmented system with the B involved, if they're equal, then my system has a solution. So in this case, you can see that whether I have this column or not, the rank is still going to be the same. And so this system has a solution. And from this point here, because this row here is the objective, I'm going to get a distinct value for every one of them, every row. And so it's going to have a unique solution. All right. There's going to be some implications that follow from that. All right. So, but for me to complete this process, the first thing I'm going to do is I'm going to divide. So again, what we're doing at this point in time is we're going to work out where the next pivot should be. I'm going to take out the row and the column, the rows and columns that have already got pivots in it, and I've left with that 7 and 14. So I really have only one choice at this point in time, and that is to divide that last row by 7. Given that I got this example from the textbook, it's going to be quite interesting because I actually have an answer. I'm going to see if I got it right. 1 on 7, row 3. Okay, so you notice I'm trying to write out the row operation I've done. So back when I made the mistake, that writing out that row operation allowed me to check. So I went back to the start and checked the very first row operation that changed that value, and then followed it through. Have I fixed that up all the way through? And so, like I said, this could be my row echelon form. I am now in a position where I could use back substitution to work out what this value is. Or I could go through and work out what my number is. So this one is already telling me that Z should be equal to 2. Woohoo! All right, we're on target. So this bit should now look like the identity because this bit didn't change and I'm making these two numbers 0. So it should be row 2 is equal to row 2 minus 5 on 2, row 3, and row 1. Yes. Row 1 plus 4, row 3. Okie dokie Drew. So we have 4, and we're going to take away 5 on 2, lots of 2. So we're going to go 4, take 5. It's going to get me -1. Slick. Woo. And then we're going to go -6 plus -6 plus 8. It's going to get me 2. All right. So the advantage of this is reduced row echelon form. All right. Like I said, we could have stopped back up here at row echelon form, but we've gone to reduced row echelon form, and that allows me to read this off. So we went at the start, we went from system of equations to matrix form. All right. We can go backwards. At any point in time, I can choose to just go backwards. This corresponds to the system that says x is equal to 2, y is equal to -1, and z is equal to 2. All right, that would be my solution, which according to the book is correct. I love it when I actually get it correct. does make it look like I know what I'm talking about. Hmm? So if I'd stop back here, this system would be saying x minus 4z is equal to minus 6. Y plus 5 on 2z is equal to 4. And 7z is equal to 14. So you can see how that bit would get you z is equal to 2. If I put that back, I get y is equal to y plus 5 on 2 times 2 is equal to 4. That's going to work out to be 5. Put it over the other side. Y is equal to minus 1. So I can back substitute. I could have stopped here and back substituted to get my solution. All right. Or not. Now, it's kind of interesting that we got down to the identity here. This is actually, if I can row reduce down to the identity, that's actually telling me something else. So I'm going to go back up to the top because I want to try and put it on this page for preference. This system here is looking like AX is equal to B. All right. Because my matrix, we've shown my matrix to have full rank. So we'd refer to that as having full rank. That actually says that A is invertible. I'm pretty sure I saw that in your notes. Yes. So if I have a square matrix where I can, when I row reduce, I get a non-zero, every row is non-zero, has a non-zero element. That means A inverse exists. All right. So we have, and so we can say X is equal to A inverse B. So just trying to connect this idea that I could have got this. So the reduced rational form, I did the same things as would have got me the inverse, all right? By doing that with those row operations, I got to a system which actually has done. Have you done a thing where we use row operations to find the inverse? That look says no. Good, not going to talk about it. All right. There's a disclaimer here. So not part of your course. There is a technique for using row operations to finding the inverse of the matrix. All right. But like I say, I'm not going to go into it. Just going to focus on the rank. What I'm going to do is I'm going to have a little bit of a look through the book and see. Actually, I'm going to pause and go. Do you guys got questions? No. Right. All right. So I want to. There we go. So I'm going to try and do this all again, and I'm going to try and be a bit quicker about it this time. But I've got x plus 2y minus z is equal to 3. I've got 3x plus y is equal to 4. And I've got 2x minus y plus z is equal to 2. Okay. So we're going to go straight to our augmented matrix. We've conveniently already got a 1 up here. So I'm just going to go that row has got my 1 in the right spot. I'm going to use it as a pivot. I'm going to make this element 0 and this element 0. Row 2 is equal to row 2, take 3, row 1. Row 3 is equal to row 3, take 2, row 1. And so 1 take 6 is going to get me minus 5. 0 take 3 lots of -1 is going to get me a 3. 6, sorry, 4. 4, take 9 is going to get me 5, -5. Yeah, sure. Then I've got so this one take so -1 take 4 is going to get me -5. 1 plus 2 is going to get me a 3. 2 take 2 take what's that? 2 take 6 is going to get me -4. Okay, sure. Now, I can't help noticing at this point in time that this little bit here, now look at that bit's the same. So I'm actually going to skip a bit, right? Normally I'd make this 1, all right? But I'm going to skip just a little bit, all right? I'm going to go 1, 2, -1, 3. And you can actually change the order in these things if you want. And I'm just going to go row 3 is equal to row 3, take row 2. And so that means that's going to be 0 and that's going to be 0. And then I've got -4, -3, -5. It's going to get me a 1. Okay. That thing there is already telling me that the rank of my A is 2. The rank of my AB, my augmented system, is actually, we can see is going to be 3. And so we know there's, well, and so this is actually telling me, so we're going rank A is equal to 2, rank AB is equal to 3. That bit there is saying, therefore, no solution. All right. And this also means, all right, that A is not invertible. All right. I'm actually putting that down because it does, we don't do it so much, but it's a useful thing to sort of connect the reduced rational form with whether the thing is invertible. All right. Because we know there is no solution, or possibly there would be possibly when I get this, when the thing is not full rank, the matrix is not invertible. If the matrix is invertible, we'd have a unique solution. We could work out what that is. All right. At this point in time, we can go, all right, that's as far as I need to go, right? I've done the thing I want to do, which is show that this system is not invertible. Okay. So I can then go, hey, done, stick a fork in me, I'm done, and just wander off, right? Yes. Oh, so possibly what we'll do is we will change the system slightly. All right. We are going to do some magic, and we are just going to rewrite this system. Haven't got this far because it's kind of useful. I'm just going to have got this far and gone, let's pretend 1, 2, -1, 3, and then 0, -5, 3, -5. Let's just pretend this is a row of all zeros. All right, I'm going to change my system to this. All right. The reason I want to do this is I want to sort of go, let's talk about finding the solution when there is infinitely many solutions. All right. So because what we've done is we've changed the rank of this AB to 2 now, that allows me to go, all right, system now has solutions. All right, forgive my shorthand for solutions. If you teach mathematics for long enough, you cannot be bothered writing the word solutions in full. That's my official excuse. So let's convert back. This is saying x plus 2y minus z is equal to 3 minus 5y plus 3z is equal to minus 5. The other row is saying 0x plus 0y plus 0z is equal to 0. Not worth putting in. So I can now do a thing where I go, I can use this equation to go, well, maybe my minus 5y is equal to minus 5 minus 3z. You know what? I really don't want to have, if everything in there is minus, I'm going to change it, just multiply through by minus 1 to make them all positive. All right, so I put the 3z on the other side. And so I'm going to say my y is equal to 5 plus 3z on 5. And so maybe I'm going to write this as 1 plus 3 on 5z. Okay. And so if I take, now I've got a value for y in terms of z. So x plus 2 by 1 plus 3 on 5z minus z is equal to 3. So x is equal to 3 plus z plus minus 2 by 1 plus 3 on 5z. All right, I just put everything but x over the other side. Let's be a little bit careful about this. So I've got 3 plus z. Notice I'm always like, it's good to look at your writing and be critical about it, right? So my handwriting is rubbish. We accept that. And so I've gone to the trouble of making sure I strike my z so that I know the difference between a z and a 2. So here's my 2, here's my z. Spot the difference. You can't. So I can simplify these things down, all right? So my 3 minus 2 is just going to be 1. My 1z minus my 6 on 5z will leave me with minus, I'm going to write it as z on 5. All right, and so I can write my x, y, z as, well, my x is 1 minus z on 5. My y is 1 plus 3 on 5z. And this number should just be z. Okay. So I can actually write my system. Is that better? I can actually write my system in terms of a single variable. Sometimes what we do, I'm going to try and squeeze this in, we'd put the numbers separately. And we might change my z to a parameter t. This is going to be difficult. 1 on 5, minus 1 on 5, 3 on 5, and 1. Okay. So we can do these things to work out. So we can actually, it also helps if we put it in the center so that's easier, gets in focus. So, so that's a way of talking about it, talking about things. Okay, sweet. We're going to use that. That's going to go. Set questions. Sure. What we might do now, you were talking about so you were talking about proofs. So what we'll do is we'll stop sharing for a second. I will check this. Which one were you talking about? Oh, A is invertible. We'll show that A. Oh, this is an interesting thing. Okay, there are various rules about sort of matrices, right? So this is a what I'll do is I'll go back to, where's Zoom go? Okay, so if we've got, the question actually is, we want to show that is equal to A inverse squared. Is that the right way around? Yes. So when we think about what's actually involved, right? So there's actually a thing that says if A times by B is equal to the identity and B times by A is equal to the identity, then B is equal to A inverse. So for square matrices, there is the inverse is unique. All right. Okay. So there is only one matrix that will do this. Okay. If I want to think about, if I have A squared, so this is setting what is the matrix that I times by A times A squared by to get the identity. If we think about A squared, that is literally just a shorthand for saying that, right? So if I start with A times A, if I times that by A inverse, that's going to get me A times by the identity. So if I then go, so A times A times A inverse times A inverse, then I can just go, that's A times by I times by A inverse. And the inverse, I can just, the identity, you can just sort of ignore. And so that's equal to I. So this is actually saying this matrix is actually the inverse of A squared. We're going, this literally says A squared times by A inverse times A inverse is equal to the identity. And I could put it on the other side just to prove my point. So I could go A inverse times A inverse times A times A. And that's going to get me A inverse times I times A, which is equal to A inverse times A, which is equal to I. It's doing the thing that we said makes it the inverse. All right. So this question is actually, it's both very hard and very simple. All right. Because you have to, they're actually asking you to do this. All right. So when we're asked to prove something that seems obvious, we're actually asking it to come up with a plan, right? We want you to go back to the definition. That's why we put down the definition of what it means for it to be an inverse, to make it so that this makes sense as an answer for this question. All right. So for example, okay, so to finish this off, we should go, so therefore, A squared inverse is equal to A inverse times A inverse, which we would write as A inverse squared. All right, we should finish it off. All right, that's like the conclusion. That's me going, hey, I did this bit of calculation that demonstrated that this matrix is acting as the inverse. Because I know the inverse is unique, I'm only getting, this must be the inverse. So so we're talking about, you mean like here? So what I've done is I'm just sort of going, hang on, this is just going, if I times A squared, so this bit's A squared, if I times that by A inverse, I can regroup. So there's actually, it's called an associative law, all right? That sort of says, It is actually in your notes because I read your notes last night. So, and if I have A times B times C, what I can do is I can group them, but that grouping can be changed. I have to do adjacent matrices. So I can, A times B times C is like doing A times B times C. Or equivalently, it's AB times C. All right. And so when I've got this, I might have had this as a single matrix, but I can sort of go, I could group it differently. All right. And so that's why that's how we can change this around so that we can group the A and the A inverse together. And so that's what I've been doing here. I've sort of gone, I've got different groupings, but let's sort of break apart the groupings. Let's sort of interpret what the notation is saying, and then go, let's write it this way. That's A squared times A inverse. Yeah. Yeah. We can literally do that. This is literally what they want as an answer, I reckon. Okay, hashtag not your lecturer, don't mark the exam. If I set this question, this would be the answer I would be expecting. So there are other things we could do. So one I saw from first year maths assignment was they gave you like C B minus 2 times A cubed. And they said, find the inverse. All right. Now there's a trick, and I can't remember if it's in your notes. I'm not sure if I wrote that little detail down. But if I have, so there's a rule that says A times B inverse. When I have that product, I change the order of them and I invert them. Yep. I was fairly confident I saw that, but I can't quite remember. So, but I can do next level stuff, right? So if I'm trying to invert all of this thing here is going to be, so reverse the order. So I've got A cubed inverse times by B minus 2 inverse times by C inverse. All right. So only one of these is in the final form I'd put it in, all right, which is that C inverse. So let's talk about, well, we've just seen that A squared inverse is A inverse squared. So this is actually going to be A inverse cubed. I can do that. Absolutely nothing wrong with that plan. In a similar way, this one is going to be like B. So it's going to be like minus 1 to the minus 2. And that kind of doesn't make sense. But I'm going to put it there anyway. We're going to go, what do I really mean? So B minus 2, well, we sort of decided that's actually a way of going B inverse times B inverse. And so when I try and take the inverse of that, all right, so when I do B minus 2 inverse, I'm going B inverse inverse times B inverse inverse. And my rule says that B inverse inverse is just B. It's like I'm multiplying. So with normal indice laws, I'd be multiplying the powers. It's actually saying the same thing works. Okay, so we've got A minus 1 cubed times by B squared times by C inverse. And so this would be the correct answer for this question. Technically we could say A to the minus 3, same as we did A to the B to the minus 2. All right. I'm pretty sure that's how they actually defined. So literally I think they actually did define something to a negative power. They actually defined like B to the minus 2 as B inverse times B inverse. This is assuming that they're all square matrices of the same size, that their inverse exists. Okay. Hashtag inverse must exist. So, so yes, you can do little tricks like that. All right. All right, 3 on there. All right, sweet. Okay, what was next on my list? Oh, there was so what were you asking about? What's that? Set stuff. Actually, what we'll do, we'll do this for a second. Where did that one go? Set stuff. Wonder what I've got that's then talk about. We're talking about doing like sort of
questions for the steps of the this, and then combine it and have to write what right.
Yep. Maybe what I'll do is I'll pop here so we can minor pause while we find the next example. So we're going to spend a bit of time talking about some set stuff now. So what I'll do, I'll actually just copy the sets that this book has got for me and then do some of the things that they've suggested we could try and do. And so to do this, it will be back to sharing the document camera. All right, so it is actually easier to do stuff to get someone else to do the creative work of making up a set. So we have A, which is 1, 3, 5, 8, 7, and 2. When we're talking about a set, it can make your life easier to put them in, like if you've got numbers, if there's an order to the elements that you're dealing with in the set that is sort of natural, it can make your life easier to adhere to that order. So see how with my set A, I've got 1, 2, 3, 5, 7, 8. So maybe what I'm going to do is I'm going to write that out. And similarly with B, just to put them into the same order. So with something like this, where it's actually not overly complicated, we can actually sort of not do this sort of thing. But it's one of those things that rates as a good habit. All right. So if I'm doing complicated algebra, all right, whenever possible, I might have my X, Y, Z. Rather than writing Z, X, Z, Y, X, right? I will reorder them where it's possible to be X, Y, Z. All right. And that is so that it makes it easier to recognize when two terms are the same thing. In the same sort of way, if I've got like an ordering, like I've got a set of numbers, if I put them in increasing order so that they're all in increasing order, it's actually going to help me determine like things like the intersection or the union. All right. Because so if I talk about actually the book actually has got U is equal to natural numbers. So literally they're talking about 1, 2, 3, and we're going to stop at 10 because 10 is the last natural number that is less than 11. Okay, so that's my universal set. The reason I want to talk about universal set is if I'm doing a complement. Oh, hey, I forgot to check. Do you use the strike or the the dash for complement. Yep, cool. So when I'm talking about the complement, it's the complement within the sample space. Okay. And so literally it is everything that is in the universal set that is not in A. So if we go through here, 1, 2, 3, the first one that's not in A is 4, 5 is, 6 is not, 7 is, 8 is, and so 9, 10. All right. And so one of the things we should know is that A complement union with A should be equal to the universal set. All right. In fact, that's true of any set. Any set union with its complement should be this. The other thing to know is that A intersection A complement is equal to the empty set. All right. There should be nothing. All right. And we love sets that do this. All right. A and A complement, great, because they have this beautiful property that everything is in one set, but nothing is in the intersection. All right. That makes my life a lot easier for some of these sets. Okay. Let's talk about doing something like, well, if we talk about doing A union B, all right? So this should be the set of everything that's in A or B, all right? So 1 is in there, 2 is in there, 3 is in A, 4 is in B, 5 is in A, 6 is not in either A or B, but 7 is, and 8 is, 9 is not, and so 10, but 10 is. So you notice there's only like 2 gaps here. There's 6 and 9. There's only 2 numbers that are missing from this set. So kind of interesting. So maybe what we should do is we should go A intersection B. Now, this means it has to be in both sets. All right. So 1 is in A but not B. 2 is in A but not B. 3 is in A, but is also in B. So 3 is in A and B. 4 is in B but not A. 5 is in A but not B. 7 is in A but not B. 8 is in both of them. And 9 is neither. 10 is only in B. So in actual fact, this is my universal. This is my my intersection. So we can actually start doing these things now. What we might do maybe what we're going to do is if we do A, I'm going to do A union B complement. All right. Whoops. And I'm going to put it on the page so you can see what I'm doing. And so literally this is the things that are in the universal set that are not in the intersection. All right. So I'm treating A union B as a single set. I've already worked it out. And so that means if you have that like an intersection or a complement, intersection or a union that you need to find the complement of, ideally we find that set first because we do the bracket, the normal algebra rules apply. We do the complement first, and then we do we do the union. Well, in this case, we do the union first, and then we do the complement. And so we can run through this quickly. So as I was pointing out when I did this, there is 6 and 9 are the only 2 elements that are not in that union. And so again, if I did the union of those 2 things, I would get the universal set. All right. Doesn't matter what my set is, how I came to it. The set and its complement will always, the union of the set and its complement will always give you the universal. Well, yeah, so this, yes, they will have to give you the universal set for it to make sense. So like I say, in this question, they literally said the universal set is natural numbers less than 11. So yeah, we can, and they have to do that for it to make sense. So I've actually got A complement worked out here. Let's work out B complement. All right. I'm going to sort of run through this a little bit more quickly. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a rule that says A union B complement is equal to A complement intersection B complement. I think they call that De Morgan's law. So now that I've got, where did I have it? I have, A complement here. Sorry, I've made a mistake. I really should have written this as A union B prime, A prime intersection B prime, just to try and keep the notation that you're using. All right. So I can actually do the intersection between my A complement and my B complement. All right. So I need it to be in both this set and this set. And so, so I'm doing A complement intersection B complement, prime, is equal to. So 1 is in this set, 2 is here, 3. Have I made a mistake? Oh. Did I make a mistake with B complement? No, 3 is there. This is where I go. Did I make oh, it needs to be in both. Right, good. And so 1 is in this set, but not this one. 2 is in this set, but not this one. 3 is in neither set, so it's not in there. 4 is here, but not here. 5 is here, but not here. 6 is in both sets. 6. 7 is here, but not here. 8 is in neither set, but 9 is in both sets. And that is the last value. And so you're actually noticing that this bit here is equal to this bit here. All right, whoops. Okay, so you can actually see that this is actually showing that thing. There's actually a similar thing that says A intersection B complement is equal to A complement union B complement. I won't go and show that one, but this would be how you'd go about showing some of those things. I can do more complicated things, right? So I'm going to pause there. You're okay with? Yep. Going to just do one more thing here. So you can get more complicated things like doing A intersection B union C. So again, the first thing I'm going to do is work out B union C. This is my problem. I tend to write the thing I'm saying, even if I've gone past it. And so if I'm looking at the union, I've got 2 is in one of them, 3 is in this one, 4 is actually in both, 5, 6 is here, 7 is not, 8 is, and 10. So now if I want to do the intersection of this set with A, has to be, so A intersection B union C. So I want it in both these two sets. So has to be in both sets. So 1 is not, but 2 is, 3 is, 4 is in 1, 5 is in 1, 6 is in 1, 7 is in 1, 8 is in both. But that is it. All right. So, and hopefully you can see the value of actually trying to put these in order, because that allows me to go through a little bit more easily to work out whether it is or is not in the set. You're allowed to do a bit of pre-processing on your calculation to work out what's going on. Times 10, up to page 4. Okay. Okay. Now, there was So I wanted to actually spend just a little bit of time going on about linear independence and what constitutes a basis. All right, just because that was one of the questions that was asked by email. So I'll go through that. Was there anything else you guys wanted to talk about? Yeah, sure. What I might try and do is do a little bit of that. We might sort of try and do sort of an example of finding critical points for a multivariable function, and we might try and do a bit of Lagrange multipliers. Don't know. I have. Did we talk? Did you talk? I thought. Did you actually talk about Lagrange multipliers in the end? Haven't heard the term. That total differential you talked about. No, you didn't. Okay. That would make my life easier. Cool. I will. Okay. So let's click on something that I can pull out fairly quickly. Because I would not order before we got to the fantasy. That I tend to show that they can already independent part. We got to order before we went back to the fantasy. Right. I got told some of them but that it's easy to do fantasy, but you know about it. Sure, we can definitely do that. What we might do, I don't know that page anymore, but I do want. Oh, hey. What we'll do is we'll actually go, if I'm going to take some vectors, I'm going to call it V1 is equal to, let's do that one. So I'm going to write them as columns. The problem with doing this sort of thing is I don't know whether I'm going to get something that's going to work out nicely for what I want to do, but I'm going to give it a go. And okay, so I'm going to start with my three vectors here. Notice I've got three vectors in R4. All right, so there is actually a thing that says the maximum number of vectors in R4 I can have that are linearly independent is 4. I've got less than that, so it's possible these ones are linearly independent, and fingers crossed they are. All right. Now, definition of linear independence says if my equation C1 V1 plus C2 V2 plus C3 V3 equals 0. All right. So if my equation C1 V1 plus C2 V2 plus C3 V3 equals 0 has only the trivial solution, then this set of vectors V1, V2, V3 is a linearly independent set. Kind of been a little bit pedantic about the language there. Not very pedantic, but a little bit. All right. Linear independence applies to a set of vectors. Okay. So we need to make sure we're applying the term to the correct thing. All right. But in this case, so what this means is, all right, so if I'm going to go C1 by -3, 0, -1, 3, plus C2 by 2 minus 2, 6, 2, plus C3 by 1, 2, 8, 4 is equal to 0, 0, 0, 0. Okie dokie, Joe. What I'm going to do is I'm actually just going to expand this out. All right, so I'm going to go -3 C1 plus 2 C2 plus C3 is equal to 0. There is 0 C1, so it's -2 C2 plus 2 C3 equal to 0. Minus C1 plus 6 C2 plus 8 C3 is equal to 0. And 3 C1 plus 2 C2 plus 4 C3 is equal to 0. Now, all I'm done there is write out equations which correspond to equating coefficients with the equating components of the vector. All right. This is the equation that tells me the first component. This is the second one, third component. All right. This means my system of equations looks like -3, 0, -1, 3, 2, -2, 6, 2, 1, 2, 8, 4. And I'm going to make it an augmented matrix by whacking the zeros down the side. Now, the key point about this is V1, and this is V2, and this is V3 as columns. All right. This thing here helps me see that my vectors go into this system as columns. All right. Going to make my life bucket loads easier that way. Now, how I'm going to do this, all right, is I'm going to actually do row operations on this system of equations. All right. What's that? Yeah. So the thing is, if I swap the rows, I'm going to change the space spanned by the rows. All right. So if I swap, like if you pretend I swap the middle two rows here, I've actually changed the space that's spanned by the rows, but it's still going to tell me if my vectors are linearly independent. All right. So there's a trick. So I could put these in as row vectors. All right. Then the row operations won't change the space spanned by those rows. If I put them in as columns, then it will change that space. All right. But if I put these in as rows, I'm going to get a different answer to whether this has a unique solution or not. All right. So that's why I need to go, oh, I actually need to put them in as columns to sort of work out if I'm going to get the thing. So there's a little bit of a nuance involved in this. All right. Interestingly enough, I might actually try and do, so again, I'm going to do this as quick as I can. In actual fact, the first thing I'm going to do a couple of dodgy things. All right. I'm going to put my third row up to the first row. And then I'm going to leave my second row there. And then I'm going to have -3, 2, 1, 3, 2, 4. All right. There is some things in here that I'm going, I feel like I can make my life easier by just nah, we'll do it the hard way. So sometimes when I see this 3 and -3 stuff, I go, oh, I could just add those together and get a 0, but I won't do that this time. That's a bad plan for this level. I am going to divide this through by -2. All right. So I'm going to have that 1 and that -1 and 0. So I did row 2 is equal to row 2 times by -0.5. And row 3 is equal to row 3 plus 3 row 1. and row 4 is equal to row 4, take 3, row 1. Okay. So come down here. So it's like 2 minus 18. So it's going to be minus 16. That's going to suck a little bit, but anyway. 1, take 24 is going to be 23. Take 23. Sure. Whole lot of numbers that we don't like very much. And so here we're going to go this one. So this number is going to be 20. And this is going to be 4 plus 24 is going to be 28. Whoa, nobody loves these numbers. But we really don't care that much. Okay. I've already got my 1 in the right spot. I was kind of lazy that way. And so this is where I just need row echelon form, not reduced row echelon form, because the row echelon form is going to tell me the thing I want to know. I don't need to go that extra step. Because I'm about to use row 2 to do something, because I've got a 0 in that first column, it's not going to change anything. That's why we did this. So we're going to go row 3 is equal to row 3 plus 16, row 2, and row 4 is equal to, row 4 is equal to row 4 minus 20, row 2. So we know with these row operations have been chosen to make that 0. This is it's all 0, so it's going to stay all zeros. And so I am going to get, so I've got minus 23 minus 16, which is going to be minus 39. Horrible number, but nobody really minds. I'm going to have 28 plus 3. Sorry, wrong thing. 28 plus 20. 28 plus 20 is like 48. Sweet. All right. I'm actually going to go at this point in time. I actually know that I can divide through by minus 39, make that 1. And so I can make that 0. So I know the system is going to have that sort of 1, 0, 0, 0. I'm going to say minus 6, 1, 0, 0. And I know that I can make that 1 and make that 0. I'm not going to change these numbers. So I can actually know that this system, and that's telling me unique solution. Yeah, so if we think about it, I want the number of columns of A to be equal to the number of non-zero rows, or the rank. All right, that's the thing that tells me, that is literally what your note said, which is that if the rank of the system is equal to the number of columns of your matrix A, then the system has a unique solution. All right. What's that? So, I mean, like I could work out what those values are by back substituting, but this says C3 is equal to 0. If C3 is equal to 0, C2 must be equal to 0. If C2 and C3 are equal to 0, C1 must be 0. And so I can go, hey, this thing I know this has a unique solution, which is the trivial solution. All right, unique solution. Equals the number of columns, yes, of that matrix, the matrix A part. So in actual fact, quite often if you see, so I've put in the zeros, but notice how that final column is always just zeros. I wouldn't bother putting it in normally. Because it's zeros, it's always going to stay zeros. If I do my row operations, putting it in is just extra writing, so I don't need to put it in. All right, so unique solution. And so I can go, therefore, V1, V2, V3 are linearly all right, we're not left enough room on the page to write linearly independent. There we go. We have almost. Okay. So this is a way of showing these vectors are linearly independent. All right. And so this applies to any dimension. What you are going to see though, right? If I have more vectors than I have dimension, so if I was to have 5 vectors, I must have a free variable. All right. Must have a free variable because I can only have the number of non-zero rows can only be 4. There must be one, at least one, that's a free variable. All right. And so that would mean that if I have more vectors than the dimension, all right, these things here. The other one that's a bit of a trap, all right, if I whack in 0 in there anywhere, if I whack in the 0 vector, I've got a column of all zeros, and that's going to correspond to a free variable. That's a variable that is unconstrained, and so column of zeros or a vector, if I include a set of the 0 vector in any set, that makes that set of vectors linearly dependent. So those are a couple of the classic things that we do to sort of go, hey, check out this trick. We are literally trying to trick you. Okay, so that would be the last of the sort of, matrix sort of thing. Oh, I did want to talk about how to show something is a basis. All right. So we're up to page 6. Okay, this is actually a bit tricky. All right, there's a bit of a trick to doing this. I love the idea of this. So what I'm going to do is I'm going to start. You guys haven't talked a lot about planes and stuff, but I'm going to just I need to sort of talk about the space I'm trying to span. All right, in some way. And so if I have a vector, if I have a plane, which is like x plus 2y minus z, I need it to be equal to 0 for this to be a thing. All right. So just take it on faith that I need it to be 0. Right. So what I'm going to do is I'm going to propose a couple of bases. All right. So if I go 1, 0, 1, and I don't know, 1, 1, minus 3. All right. How would I know if that's a basis? All right. Now, any ideas? Any guesses? Sure. Sorry. Could try and do, so one of the tricks is when I'm trying to show something's a basis, it's actually a bit of a trick. It's actually a lot harder than it might sound. What's that? Yeah. So they span a space of dimension 2. All right. They don't span R2. All right. That thing, so there's a fancy mathematical term called isomorphic 2. So it's equivalent to R2, but it is not R2 because it's a version of R2 in a higher dimension. All right. That's actually a really key point to talk about here, is that 2 vectors span a space of dimension 2, but in a higher space. The first thing we should address is, are they linearly independent? All right. So what I'm going to do is I'm going to go C1 V1 plus C2 V2 is equal to 0. Let's suppose this is my equation. What this is actually going is I can rearrange this to say C1 V1 is equal to minus C2 V2. or V1 is equal to minus C2 on C1 V2. If C1 and C2 are not both 0, all right, then V1 and V2 must be a scalar multiple of each other, scalar multiple. So for two vectors, all right. All right, there's a little bit of a caveat that if V1 or V2 are 0, then that would make them linearly dependent, but that's your case where K is equal to 0. So I can actually look at these vectors and observe that they're not linearly dependent. All right, I'm allowed to observe that they're not linearly independent. So 1, 0, 1 and 1, 1, minus 3. All right, sweet. So we know they're linearly independent. We know they span a space of dimension 2. We also kind of know this thing is of dimension 2. Okay, so there's a trick, right? If I have the right number of vectors that are in the space and are linearly independent, they must be a basis for the space. All right. In this case, the only thing I haven't shown is that they're in the space. All right. And so what I do is I just put them in. So this would be going, all right, 1 plus 2 times 0 minus 1. That's equal to 1 minus 1, which is equal to 0 in the space. If I go, what's that? Now, so, yeah, so this is actually a trick, right? I could do this and go, if there were orthogonal, so if I have a set of vectors that's mutually orthogonal, so every pair of vectors is perpendicular to all the others, sort of thing, then I would be having, then I could say that this set would be a linearly independent set. But I still have to go through, for it to be a basis of a specific space, the vectors must be in that space. All right. And so, yeah, so, all right, this is equal to 1 plus 2 plus 3. All right, not in the space. Oh my gosh, not a basis. Sorry. So what I've done is I've treated, this is X, this is Y, this is Z. So I've gone, so what I'm doing here is I'm going 1 times X, 2 times Y, minus 3 times Z. What's that? Because X, Y, Z here don't satisfy this equation. All right. All right. I'm defining my space. Possibly we should go X, Y, Z in 3 such that. All right. We could do that. That might be a thing. Yep. So what I could then do is I could then go, all right, let's take my set of vectors, which is 1, 0, 1. And So I'd only have to change this to this vector. These are still clearly linearly independent. They're still the correct number. And this vector is now in the space. So therefore, this would be a basis. So I'm allowed to argue that they're not a scale because there's only two of them. I'm allowed to observe that there is no scalar multiple of this vector that would give me this vector. Yep. Yep. So you're actually allowed to know that. All right. You are allowed to know that. So you were talking about, so there's actually a trick, right? You go, hey, Nick, couldn't I choose orthogonal vectors? All right. So what I've done when I've created this is I've actually looked at this equation up here and gone, in actual fact, what I did in my head is I said, oh, I'm going to make x1 and y0. What will z have to be? And then I made x1 and y1. And then I thought, oh, what I'll do is I will choose it to be not correct, but I'll choose it to be a nice simple fix to make it so that it is in the space. Because I actually wanted to show what would happen is, because they'll do this. Maybe, I don't think there are things that mean actually, but they might go, is this the basis for this space? Okay, let's check the things that I need to do. So one of the things about checking something is that forms a basis for a given space is that vectors are linearly independent. They're in the space. There is the correct number of them. The number of linearly independent vectors I have matches the dimension of that space.
There was a question about this.
Yep.
Basically, it's in marks at the end of sales. Show that they were to show that they were that they would quite a lot of
yeah.
After that, if sales, because they're independent, I can't exactly because they're independent against the way then that is their information. You didn't actually have to show them.
Yep. So if you've got a space like I've got here that is not all of R3, all right. So if I was to give you a basis for R3, all right, then you would have to go, I need three vectors, I need them to be linearly independent. All right. And if I have three vectors in R3 that are linearly independent, they span R3. All right. So no, if I'm trying to span all of the space, I need the correct number of vectors. All right. If I've got R4, I need 4 vectors in R4. I could, if I'm claiming it's an orthogonal basis, all right, just use that dot product. Because if I have a set of vectors which are mutually orthogonal, that means they're linearly independent. So, for example, if I was to take my set of vectors 1, 1, so what did I say? 1, 1, 3, and 1. Actually, what I really want to do, I'm going to try again. I'm going to go stick with 1, 0, 1, and 1 and minus 1. And so I'm going to do that. Pause while I check that this one is actually in the thing. So if I go 1 plus 2 minus oh, that's going to be plus 1. Nope, that's not what I want. I need to, let's see, that would be 2. Oh, I need that to be that one. So what I'm trying to do is, you notice how if I do the dot product of these two vectors, it'd be 1 plus 0 minus 1, that'd be 0. I'm trying to work out what value I need to put here because I'm going to match it with the 0 here. So by sort of going 1, 0, 1, if I go 1 something minus 1, I've got my vectors to be perpendicular, so I can actually choose vectors that are perpendicular. But I also want it to be in the space. So if I do this, I do 1 minus 2 plus 1 in the space. So this set, so if I do 1, 0, 1, dot with 1 minus 1 minus 1, which is equal to 0, this is telling I can go there. There's two vectors. They're linearly independent, and they're both in the space. They will form a basis. Yep. So I can show that I can use the dot product being equal to 0 to show that they're linearly independent. The dot product so the dot product doesn't have to be equal to 0 for vectors to be linearly independent. It does have to be 0 for them to be orthogonal. Yeah. All right. But that's that rule that says an orthogonal set of vectors is linearly independent. That says that they're linearly independent in the space. So if I say this is an orthogonal set of vectors, it doesn't form a basis for this thing. All right. So I want to show that they're orthogonal, but then I want to show that they're in the space. That isn't, and then it's just a matter of have I got enough of them? So if they're mutually orthogonal, showing that is actually showing that they're linearly independent. All right. So knowing that it's an orthogonal set of vectors is equivalent to, well, is more than knowing that they're linearly independent. All right. What's that? No, not the other way around. Linearly independent is different from, so if you imagine like orthogonal is between every vector is a right angle. All right. But I can have vectors which are almost the same direction, but still linearly independent. So linearly independent is one of these directions is not able to be found by the other two. But it's enough to sort of go, but if I can actually go, this system has whatever as a solution, then my vectors can be linearly independent. It's just that there's a high amount of sort of this vector in this direction sort of thing. So I can, the orthogonal is there is no amount of the other vectors in this direction. All right. So the orthogonal is an orthogonal basis is the thing we really want. But sometimes any basis will do. All right. If you go into the shop and the orthogonal basis is the same price as the regular basis, you get the orthogonal basis because that's the better basis. All right. But sometimes it has more cost associated with finding that basis. Okay. So we were going to talk about multivariable calculus stuff. So like I say, making up examples sucks, which is why I have a textbook. Sorry? Oh, yeah. Functions of two or more variables. Partial derivatives. Maybe I should look at that. Root. Okay. None of these suck too hard. Did you have something, a particular thing, or should I make? Yeah. Z is equal to x squared plus y squared. X squared, y squared. Okay, sure. So x plus y, not plus 1. Just like that. All right, sweet. So this one sucks, but also we're going to just do it. All right. So first thing I'm going to point out is both the numerator and the denominator are both functions of x and y. All right. And so that means if I'm doing the partial of z with respect to either x or y, I have to apply quotient rule. All right. And so quotient rule says derivative of the top line. So I'm doing a partial with respect to x. So it's like 2xy squared times the bottom line, x plus y, minus the derivative of the bottom line. In this case is just 1. So the derivative of the bottom line with respect to x is just 1. And then times the top line, x squared, y squared, all on x plus y whole squared. All right. Under the heading of stuff that sucks. So what I should do is I should simplify this a little bit. All right. So I've got my 2x y squared. So that when I times by x, that's 2x squared y squared plus 2x y cubed. And this is going to be minus x squared y squared on x plus y squared. And this one is the same as this one. So this is that thing where I was talking about earlier about putting them in order. I've got an x squared y squared. I've got an x squared y squared. I can sort of write that as x squared y squared plus 2xy cubed on x plus y squared. Woohoo! That looks like a nice expression. So dz dy is equal to, so again, derivative of the top line. So it's like 2x squared y times by the bottom line, x plus y, minus the derivative of the bottom line. Again, that's just 1 times by the top line, x squared y squared, all on x plus y whole squared. Notice how I didn't expand out the denominator. All right, pro strat, never expand the denominator. All right, generally speaking, I did actually look and go, oh, could I have taken out an x plus y from here somewhere? And possibly I could have, but it wouldn't have worked. It wouldn't have done that. So expanding this out, 2x cubed y plus 2x squared y squared minus x squared y squared. So hey, same sort of thing happening. And we kind of figured, given, so this function is actually symmetric in x and y. So we kind of figured that it would actually look that way as well. So 2x cubed y minus plus x squared y squared on x plus y whole squared. All right. Sweet. Okay. Everybody happy with that? So that's relatively simple. Now, I say relatively simple. What we'd want to do then is go, hang on, where are my critical points? All right. This is quite a challenge to do this one for where are the critical points. And I don't think you'd be asked to do something this complex. So, but we would be finding where both of these are equal to 0. All right. So if I just take this one here, if I go 2x cubed y plus x squared y squared x plus y squared. Now, I have a thing where if x is equal to x is equal to 0 and y is equal to 0, that would be 0 and 0. That's technically undefined. I don't want that. All right. That would be 0 divided by 0. World of undefined. I could do something. I could actually go through a thing about continuity. You know how you talked about continuity as a single variable? Sure. At this point in time, I'm going, I'm sure it's your course, but I can't. I've done 4 different subjects. This is the 4th subject in consecutive days, which are different, but not a lot different. So I'm just like, I'm sure you had a definition of continuity for a single variable. You didn't do anything about this for multivariable. What I would do with this is I would try and factorize. And so I'm noticing that each term on this numerator has an x squared and a y. So I'm going to go x squared y. And what I'm left with is this is going to be 2x and this is going to be plus y. All right. So what I take from this is x is equal to 0 or y is equal to 0 or 2x plus y is equal to 0. Okay? So I'm focusing on that numerator and I'm going, x could be 0 or y could be 0 or 2x plus y could be 0. All right. And so this one I could say, well, maybe y is equal to minus 2x. So what I'd do if I'm actually trying to solve this is I've used the partial derivative with respect to y. I would try each one of those in my partial derivative with respect to x, the other partial derivative that I've calculated. All right. And that will allow me to see if I've got something. So if I go dz dx and I evaluate x is equal to 0. All right. So that means here, what I've got in that numerator would be 0 plus 0 on y squared. That'd have to be equal to 0. All right. So in actual fact, because I want everything except for where y is equal to 0, y not equal to 0, that would actually get me x is equal to 0. That's actually getting me the y-axis. Oh, sorry. Yes, that would help a lot. Thank you. Similarly, if I do this, so if I do my partial of z with respect to y, evaluated when y is equal to 0. All right. Again, I'm going to get 0 on 0, 0 plus 0 on x squared. And so x not equal to, that's equal to 0. X not equal to 0. I want to avoid that thing. And so that's the y-axis, x-axis. Y is equal to 0, x-axis. All right. So now if I put in this other constraint, so if I do dz on dx evaluated when y is equal to 2 minus 2x. All right, this is a horrible thing. So I'm going to go x squared by minus 2x whole squared plus 2 times x times minus 2x cubed on x minus 2x whole squared. Well, there's a lot of x's, man. So this is going to get me x squared, so times by 4 times by x squared. This is going to get me plus 2 times x times minus 8x cubed. This is minus x whole squared, so I'm going to go minus x whole squared. So that's 4x to the 4, and that is minus 16x to the 4 on x squared. Oops, right down here. All right. So by taking this constraint and applying it down here, that would actually, the only way that's equal to 0 is if x is equal to 0. And I don't want that point because that point is, the function may actually be continuous at that point, but I can't talk about that. So what I've actually got is I've actually got critical points along both the x and the y axis. All right. And that's just a way. So that means that my function is flat along the x and y axis, whatever it happens to be in the other areas. All right. And so if you imagine, actually, it probably does a nice little, I'll put the page over and try and do this. So because along your x and y axis, it's got to be 0 along here and 0 along here. Because what we're doing is we're sort of, it's probably going to come up and then it's going to come down. And so if you imagine it, it's a bit like a Pringle. It's a little bit like a Pringle, where you've got the sort of one edge is going down, one edge, so one edge is going up, one edge is going down, and so it's going to get me. And so maybe this function is continuous at 0, and so maybe it's flat at 0 as well. Maybe 0, 0 is a thing. That's a completely different question to talk about. Okay. Yes, we're happy with this plan. Do we want to try some more multivariable functions? This is that. So this is that thing where I wasn't actually,
Wait, you never showed up.
yeah, I'm looking at that and going, I'm not 100% sure. You did things about, there's things like small increment formula. Did you talk about the small increment formula? Okay. And also, so there was like, what was it? Marginal product. So marginal utilities, marginal product of capital and marginal product of labor sort of situations. They're different. So if I've got like my Cobb-Douglas production function, then my marginal product of labor is just a way of talking about the partial derivative with respect to labor. There is a thing called the total differential. Yeah. So total differential, this was there are other reasons. Yeah, so total differential was on my list of things to talk about because the total differential actually gets used in some of the macro model. All right. So what I'm going to do is I'm going to take an arbitrary equation out of this book just because I can. I don't want to get it too complicated, so I'm just going to go my z is equal to x squared plus 6xy plus y squared plus 16x. Okay. So my total differential would be like dz is equal to the partial of z with respect to x times by a small change in x plus dz on dy times by a small change in y. Okay, that's actually the formula for my total differential. So let's do my partial of z with respect to x. So here, that's going to get me just 2x. With my 6xy, remember y is being held constant. So it's like the same as the 6. So this is actually going to be 6y. If this is a constant, when I differentiate with respect to x, it goes to 0, and so I'm going to get plus 16. Partial of z with respect to y, same sort of thing. That's 0 plus 6x plus 2y. That's my thing. So my total differential, my dz, is going to be equal to, I'm going to put this in brackets. It's really important to remember the brackets for this sort of thing. Plus, and then 6x plus 2y dy. Now, this is where the plan for an implicit derivative comes in. All right. You've seen the implicit derivative thing somewhere, yeah? Nod wisely and say yes. Yes, Nick, maybe you have. So if I set dz to be equal to 0, so what this is going to do is if I have my level curve, my indifference curve, right, I can get the slope of the indifference curve by setting the change in z to be 0. All right. And so that means we've got 2x plus 6y plus 16 dx plus 6x plus 2y dy equal to 0. So what I'm going to do, I'm maybe going to put this over the other side. 2x plus 6y plus 16 dx is equal to minus 6x minus 2y dy. I want to put this dx with this dy. So I've got my 2x plus 6y plus 16 is equal to minus 2x minus 6x minus 2y dy on dx. This is actually the thing I'm trying to get, all right? I'm actually trying to get this particular thing. I want to get it by itself, so I'm going to divide through by this. And so I'm going to have, and I'm going to do a dodgy trick where I switch it over. So I want to say dy dx is equal to 2x plus 6y plus 16 on minus 6. At some point in time, I'm going to give up. Possibly, I would put the minus on the top. I would write it like that. Okay. So, just as a bit of an aside, so quite often you'll say your formula for dy on dx is actually minus the partial of z with respect to x on the partial of z with respect to y. All right. That I'm confident is in your notes because it's in my notes and I wrote your. All right, so for my indifference here. What's it? Marginal rate of substitution? Yes. Yes. So they do like to refer to it as your marginal rate of substitution, yes. Which is equivalent to the slope of your indifference curve.
And when you're actually using that function, you have to make the first part negative. Like you have to put it negative.
So this formula, so if you look at what happens, that negative came from putting the term on the other side of the equation.
But if you were just given like one equation and then you found the partial with respect to x, you have to put negative down.
Yeah. So to find that marginal rate of substitution, so you notice how I kind of put the minus from one bit to the other bit. It doesn't matter actually which one we put it with. The convention is we put it with the thing in the numerator, right? So, yeah, if everything in my denominator was negative, I'd slip it into the denominator so everything became positive. Because this is like a utility function, I would just leave it as it is. Yeah, so if I've got a particular point, on my utility function, I could sub in those values. I would actually get a rate of substitution. I would actually literally get something which would tell me, so it literally tells me the slope, but that literally tells me, I could, so many X is worth so many Y. And so that's, how many chocolate bars am I prepared to trade for a can of Coke? So, and that depends on my utility bundle and my type of my indifference, my type of utility function. Okay. Have we got more questions? I feel like this has been a really good session. Thank you guys. It is on the 2 hours, so I'm actually going to pull the pin at this point in time, unless you guys have got more questions. So, this video will go up on our website. So if you go to the Maths Learning Centre website, so adelaide.edu.au/mathslearning, if you click on the bit that says resources and then find mathematical economics, you'll see some of the past revision seminars. You'll also see this one come up in the next couple of days. Good luck with the exam. Come and talk to us upstairs in the Maths Learning Centre. What's that?
Is it double time to say? Is it still 10 or is it 1?
So this week it's 10 till 4. Next week we're going 1 till 4. I'm going to stop this recording now.